All right, so again, so the question sort of came down if you're making a sort of polypeptide. I guess this is just a tripeptide. It's just a small sort of peptide sequence, but we hadn't really discussed this that much. But you guys had the course with Guillermo, and so sort of what came up was, well, what kind of questions can we potentially expect to get? And really, as I sort of stated last class, what I view peptide synthesis from a synthetic chemistry standpoint, one of the values of it as a sort of thought experiment is to get you guys considering this idea of orthogonal protecting groups, right? So we discussed last week, I'm not going to basically throw them all up here, but I'll just sort of mention them very quickly. That sort of so we basically have seen three different types of deprotections that we can see. One of them is under acidic conditions. So the acidic one for amines, it's sort of Bach, and so again that's the tert-butyl one, right? So that's the one where when it cleaves, you have a tertiary carbocation. So under acidic conditions, you should be able to sort of show that mechanism and explain why it's acid sensitive. Base conditions were the FMOC ones. Again, that one was the one that was a fluorenyl, so it had the two aromatic groups and the sort of acidic proton between the two benzene groups, which after deprotonating allows for you to do the elimination. So again, you should be able to sort of know that mechanism, for example, of why that would be deprotected under acidic conditions. The one that's a little bit more tricky from a mechanistic standpoint, and again, I sort of admitted I'm not even entirely sure what the expected mechanism of it is, but it's a hydrogenative condition. You can certainly do a mechanism where you hydrogenate one of the double bonds on the benzene and then do a series of rearomatizations to sort of cleave it, and that's what I used to think that it was until I started actually doing the chemistry and realized that that you can deprotect these benzyl ethers even under things like with other groups around that would likely hydrogenate. So it comes off a little bit slower. So I think it's about the ability to cleave, and so just sort of direct hydrogen across the sort of oxygen-carbon bond or the oxygen-benzylic bond. We didn't sort of go too much into depth on protecting the carboxylic acids, but it's very analogous, at least for the acid and the benzyl one. So you can protect carboxylic acids as those as sort of T-butyl protecting groups. CDZ, likewise, again, it's a benzylic one, and so for those same reasons, you can deprotect benzyl ethers under hydrogenated conditions as well. As some of you have seen in the book, these will come off under partially acidic conditions as well, so you can certainly cleave benzyl groups under acidic conditions, but let's not worry too much about that. Let's just say that you can definitely cleave these guys under conditions that won't cleave these. So this is more susceptible to acid than this, even though you can, in principle, cleave that under acidic conditions. You could probably imagine you could also cleave that under basic enough conditions as well, right? If you had, say, for example, sodium hydroxide or something like that. But the point is that you can cleave that under hydrogenated conditions. From the standpoint of the basic one, people generally don't put fluorenyl methanols. While this is analogous structurally, right? This is the benzyl part is the CDZ part. The T-butyl part is the same as the Bach. We don't generally think about putting fluorenyl groups on esters. It's just not something that's done. For your guys' standpoint, probably the one that I usually just show to be the analogous one would be the easiest to hydrolyze ester, which would be the methyl ester. Again, it's smaller, it's more accessible to like sodium hydroxide, so it would be slightly different conditions. But anyway, so this is the point, is that you have this sort of group here that you can use under different conditions. And so the question that I posed for you guys last class was propose a synthesis of this from individual amino acids, and those individual amino acids, I basically told you could start with any protected version of the amino acids that you wanted to. So the first thing that we would probably want to do in this problem, though, is just start by asking the question, what are the amino acids that we're going to start with? And that should be fairly straightforward, right? We'd simply look at where the amide bond disconnections take place. Because in peptide synthesis, it's the reaction between an amine and a carboxylic acid that is going to ultimately make the amide bond. So any place that you see an amide, right, we're going to sort of cleave that bond. The amine will be on the left-hand side, and then on the right-hand side, we need something that's there, and that's the carboxylic acid, right? So we can look at each of these positions, and that's going to help us identify the carboxylic acid, the amino acids that we're going to start with. So in this case, we have glutamic acid, which is that one right there. Glycine. And then I guess I don't think this is ornithine that I've drawn there. Okay, so these are the 3 amino acids that we would need to start with. But the point here is that we can't simply take these and do couplings, right? If we were going to start making this molecule, right? If we wanted to start with this guy, and then say, for example, couple this molecule with this molecule, and we want to make this amide bond, right? That's not going to be a selective process, right? You're going to get a whole bunch of mixtures, right? In addition to this amine reacting with that carboxylic acid, this amine could then react with that carboxylic acid to make an amide. Some of this molecule could react with itself to make these sort of homodimers rather than the sort of heterodimers. We could start getting functionalizations of this carboxylic acid. So there's a lot of things that can happen here. So in sort of peptide synthesis, what you need to do, right, is you need to bring in these molecules with the appropriate protecting groups. Now, as I told you guys last week, sometimes when I ask these questions, and I've asked them in the past this way, I will give you the amino acids, and I'll sometimes throw protecting groups on there. Okay? And given the time, that's probably what we'll do. We won't worry too much about physically putting on the protecting groups. But we have to sort of choose the ones that are going to be wise to use, right? So we can start and make, from this standpoint, we have a couple options. We actually have a lot of options. There's, I don't know how many different potential answers that would be correct in this regard, but you guys have to sort of start somewhere, and so we usually read left to right, so it would probably seem most logical to just sort of add these up from left to right. And so the first question that we're going to sort of have is, how are we going to combine these two molecules here? And if we want to selectively make that amide bond right there, then we're going to have to protect everything else on this molecule, come in with a protecting group of everything else on this molecule. The other thing that we'll have to sort of recognize, though, is that at some point we're going to have to make this bond as well, right? And so what that means is that if we're going to do this coupling and we're going to start protecting these groups, right, we're going to want to protect this, right? But we're going to want to eventually, after we do the coupling, we're going to want to liberate that free amine without affecting the protecting groups over here. So this is where the orthogonal protecting groups come in, okay? So whatever we choose to protect over here, we want to make sure that it's different than, it's going to be deprotected under different conditions than here, okay? The other thing that we sort of have to consider in this, right, and maybe we can do a follow-up if there's, I know we've got a couple other problems that we want to do today, But in this problem, it's actually a little bit simpler than some others, but in this case, we also do have the side chain. And so again, we have 3 protecting groups. As we'll see in this problem, we won't actually need all 3 of these to do the chemistry, but there are cases where we would need that third. If we have time, I'll show one, because you could imagine scenarios where, say for example, you want the side chain to be protected, and you want to deprotect that side chain while leaving everything else intact. Or you want to deprotect, say for example, the backbone carboxylic acid without affecting the side chain. And so this is oftentimes where the third protecting group will come into play, and it will mostly have to do with the side chain. It just so happens that based upon how this is written, as we'll see, we probably won't need to sort of do that, okay? All right, so when we start thinking about the amino acids that we want to couple together, if we're going to start here, we can sort of recognize as we're going from left to right, there's never going to be a need to have one of these deprotected and not the other. So we might as well just protect these as the same thing, right? That way we can protect them both at the very end at the same time, do what's sort of called the global deprotection, take those off. So we can choose whatever we want. Just looking over there at the carboxylic acids, the carboxylic acids, I'll just choose the one that's on the top simply because it's there. We'll just choose that T-butyl group, okay? And so we'll protect these as T-butyl groups. And so, because I said you could start with any protected carboxylic acid, we'll just start there. Likewise, on this amine that we have over here, we can protect that really as anything that we want. Except for one, right? We're not going to want to protect it as the Bach, right? We're not going to Bach protect it, because if we Bach protected it, then it's going to be difficult for us to remove the Bach group without also removing the T-butyl group. So we'll want to choose one of the others, and so given what we have, we'll just put the F-Mach group. Okay, and so the first step of the synthesis so the first step of the synthesis would be so we'll take those two together, and what's the reagent that we use to couple peptides? You guys remember DCC, right? Not to be confused with PCC. DCC. Okay, so that's dicyclohexylcarbodiamide. It's a coupling agent that basically couples these together. Okay, and what I'm going to do just to conserve on board space is once we couple that, right, the next thing that we can do, which is fairly straightforward, is we're just going to want to deprotect the F-Mach group. So how do we deprotect the F-Mach group? Under basic conditions. The standard basic conditions that's usually used is piperidine. It's an amine base. I'll just put R2 and H for the amine, but that's going to be the base. The amine base is going to deprotect that. But this is going to deprotect the F-Mach, and it's not going to touch the T-butyl group. So I just say on board space, I'll just put one after the other. Yeah.
Does it matter which base you use?
No. Well, in practice, yes, but for the purpose of this exercise. So yeah, sodium hydroxide would probably be fine. I mean, the issue that you run into with sodium hydroxide is that if, say, for example, you're risking hydrolyzing, in principle, you'd probably be okay with this guy because it's so sterically bulky, but you'd probably hydrolyze, say a benzyl ester would probably get hydrolyzed versus sodium hydroxide. So just stick with the amine base to be safe. So I said no, but just stick with the amine bases for this sake. I would probably be fine with it, but I could envision issues, less likely to envision those same issues with a piperidine. Okay, so just R2NH. Okay, at this point now, we have the free amine, right? So now we'll want to couple this group over here, right? And we have these two amines that we have over here. And so again, we can basically choose them already being protected in a certain way. And the question here becomes, do we want these guys to, you know, what would we want to perhaps protect them as? Okay. Now, once we do this coupling, the last step that we need to do, right, is going to be take off these T-butyl groups and take off whatever group is over here. And so this is an opportunity where perhaps the global deprotection strategy would be good as well, right? Because there's never going to be a scenario where we're going to want to deprotect these. You know, we're not going to continue to grow this chain. The target is this. Once we have this molecule there, we can basically deprotect those amines, and then we move into our final molecule. So this is a situation where you might just want to choose an acid-sensitive amine protecting group. That way, your last step can basically just deprotect everything, right? So what we'll use the Bach protecting group, which is in this case, and we'll just Bach protect both of these. Right, and so then we'll have that peptide, and then the last thing that we have to do is simply take this molecule and do a big global deprotection. So we're going to treat it under acidic conditions. Yeah.
How do we show us adding the protecting, like synthesis-wise?
So
Just show an arrow there, like off on it, like something like that.
so how do you show the actual putting the protecting groups on? So okay, so technically. So we're not going to have time to go over all of this. So I think I can sort of say that I don't think that it's going to be necessary for you to do that on the exam. Since I wrote it, I can safely say that at this point. But you still may decide to use these in a synthesis problem. If you do, using something like FMOC chloride, for example, would probably be okay, which is actually what it is. So you can sort of treat it. Somebody was asking me upstairs. You can, for the sake of now, you could, within a synthesis problem, treat it like a, you know how like if you have TBS chloride, oftentimes you won't draw out the whole silyl group. So you guys could probably do the same thing with this. So put Bach chloride, TBS chloride, CBZ chloride, and then just put NHCBZ. The T-butyl, to make this T-butyl group is a little bit more complicated. You actually use this sort of, usually the butene under acidic conditions. So the branched butene with acid, and what that does is you protonate this, generate the carbocation, which is then trapped by those. You could probably propose a synthesis of making the benzyl esters, right? And the methyl esters would be fine as well. Those same type of esterification reactions don't necessarily work as well for T-butyl, simply because it's just not a very good nucleophile. Like T-butoxide is just not a very good nucleophile. Okay. So again, the last step here would be that you would treat this to some sort of global acidic deprotection conditions. Usually the choice reagent, I don't know if you guys sort of learned this one, I think you have, is TFA. You guys know what TFA is? So TFA is trifluoroacetic acid. So that's TFA, it's basically trifluoroacetic acid. It's oftentimes the choice in these T-butyl protecting groups. The reason for that is that it's a little bit more acidic than acetic acid. The pKa of acetic acid is somewhere around like 4 or 5. The pKa of TFA is closer to 0 or 1, so it's a little bit more acidic. That helps, obviously, speed up the reaction a little bit. But the other reason is from a practicality standpoint, acetic acid is very viscous. It's difficult to get off. I think the boiling point of acetic acid is, I don't remember the number off the top of my head, but it's high. I feel like it's 120. Might even be higher. I don't remember the exact number. TFA, even though it's heavier, one of the things about these fluorines is one of the interesting properties of fluorine-containing molecules that they are actually oftentimes much more volatile. There's a disruption, I believe, in the sort of one of the dispersion forces with it. So the boiling point of this is actually somewhere around like 70 or 80. So it's a lot easier to sort of, you can just rotovap off the TFA at the end of the reaction. It's just a much easier process. So that would be ultimately the product. Okay. So this is kind of what I view from the peptide synthesis. This is what I would expect you guys to be able to do. Doesn't necessarily mean that you're going to get a question that's going to be a peptide synthesis question. But what I can tell you is that I did write a synthesis question that will require the use of these orthogonal protecting groups. But I will sort of give them to you. So, all right, and at least one of the problems. So it's not going to be necessarily exactly something like this, but it will require this idea of orthogonal protecting group and understanding what the different protecting groups can come off under. So you should know that a Bach group comes off under acidic conditions. A bent CBZ would come off under hydrogenated conditions. FMOC would come off under basic conditions, and you guys should be able to know those mechanisms. All right, so I'm going to throw up that metathesis cascade, and then I got one email from somebody that wanted to do sort of co-plays and stuff, so we'll do one of those. And then if we have time, we'll do other, we'll see how much time we have left. So as I told you guys last class, I really like the metathesis reaction, in part because from a problem-solving standpoint, you can actually have some pretty cool Okay, so the mechanism problem that we had for the metathesis cascade, this was actually on one of my one of the problems that I had. And so this was a rather involved metathesis problem that had sort of two parts to it, and so we'll just start with the first one. And so the idea behind this is at the core of this molecule, basically where the metathesis is taking place, it turns out that if you start your ruthenium catalyst at one position if you start your ruthenium catalyst here and then do a cascade this way, or if you start with your ruthenium catalyst here and do it that way, turns out you get very different products, which is kind of interesting. So one of the ways that that Tom Hoy, who sort of is the guy that really developed this idea of relay metathesis, he figured that if you built a molecule where you would basically have a more accessible alkene that would then do sort of an internal ring-closing metathesis, that would in fact relay the ruthenium catalyst into the position that you'd want. So this is a strategy that he's used in situations where the metathesis reaction might not be all that selective. And so the first step of this reaction, hopefully you guys sort of went through this. The first step of this reaction is going to be that you're going to put the ruthenium alkylidine at this position. Okay, so again, I'm not going to go through all the steps of these, but you guys should. So it would be a 2 + 2 followed by a retro 2 + 2. That is going to put the ruthenium alkylidine at this position here. And what I'm going to do is I'm just going to sort of leave off that side for now. So what we'll do is we'll just do show the ring closing metathesis, and what I'm going to show is through a mechanism, I'm going to sort of illustrate how the ring closing metathesis will leave the byproduct that I showed you guys, which is the furan, and through that process it's going to put the ruthenium alkylidine at the position seen here, okay? So when you have a molecule like this might be one, again, this is why oftentimes redrawing molecules is important, because as drawn, you know, it might be difficult to see necessarily the 2 + 2 here. So what you'll often want to do is redraw this molecule a little bit so that you can at least start to see what's going on. So I'm going to bring them a little bit closer together, and we're going to do the 2 + 2. Right, so this is the bond. If we sort of number these 1, 2, 3, 4, 5, 6. Right, this is going to be 1, 2, 3, 4, 5, 6. Right, and then from the 6 is where we're going to have everything else sort of coming off at that position. Okay, and then what's going to happen here is now we'll do the retro 2 + 2 in this direction. And that's how we're going to get the ruthenium alkylidine there. So you notice that when you do that retro 2 + 2, the alkene that's being sort of generated, that sort of goes away, is actually that furan. Does everybody see that? Okay, and then what we'll have is the ruthenium that position there. Okay, so that's how we're going to relay it over to that position. So that's the first step of this mechanism. Okay, the next part of this mechanism, right, is that now we have options. Now that we have the alkylidine here, what we're going to want to do is now do the intermolecular cycloaddition reaction, right? And this is one it's really this internal alkene and how everything sort of works out that actually pushes it in one direction or the other. So again, this is a situation where when it's drawn out here, it might be a little bit difficult to see sort of what we're looking at. Okay, so what I'm going to do is I'm going to give myself a little bit of board space. So you know what? I'm going to redraw this molecule up here, and then I'll sort of move back in that direction. So this is the problem with these. Okay. Now what we want to sort of recognize here, so this is a question that actually has come up with regards to palladium sort of cross-coupling, specifically the Heck reaction, right? So the question came up with the Heck reaction, you know, when the palladium adds across the alkene, so I've had a few people ask me this question. When the palladium adds across an alkene, it can potentially add across one of two ways, right? You have that regioselectivity across the alkene, That's the same with everything that we've seen, whether it's hydroboration, whether it's adding water across it, all these different things, you can imagine adding in one way or the other. When you have a palladium-carbon bond, if there's an R that's hanging off on one and the R that's hanging off in the alkenes, and sometimes it can be sterics that will drive it, and that's usually what we've seen for, say, for example, for a cross-hec. That's why oftentimes we get sort of the substitution at the basically not 1,1 disubstituted, but often 1,2 disubstituted alkenes, and that's usually sterically driven. But some of you guys have noticed that have studious of you that have really gone in and really done all of the work problems, which great. You may have noticed an intermolecular hec, where the only way that you could get to that product that they show, it's a mechanism question, really the only way is to sort of do it a little bit differently. And that's driven by ring, right? So oftentimes when you have a ring, and this is going to be the same here as we'll see because it's going to be a 2 plus 2, if you can do a 2 plus 2 with a ring, the sort of bonds often go what we will often call exo. So they'll often go exo, sort of like outside. So you can imagine the other one would be very torsionally strained. It might be very difficult for it to sort of adapt that. So when we're looking at this problem, what we want to do is the ruthenium can be here or the ruthenium can be there. But the likelihood is that we're going to want the ruthenium sort of both groups pointing in the same direction. So since this is going outside of the ring and this is going outside of the ring, we're probably going to want the ruthenium and the alkyne on the same face. Does that make sense? And that's because if you try to put the ruthenium on the inside, then it's really, it's forcing the ring to adapt a lot of strain to be able to get to that appropriate orientation. It's, Okay, so what we're going to do is we're going to redraw this a little bit. And this ring would be a 1, 2, 3, 4, 5, right? Not too shocking. There's a 5-membered ring there. And so the other thing that you can often do as a trick when you're sort of trying to redraw these molecules is to sort of look at this sort of ring structure that we have. So that's going to be the 5-membered ring. I'm not going to necessarily draw it as the 5-membered ring. But I'll start putting it in that position. Right? And in this way now, one of the things that we can do is we can begin to a little bit more easily see the 2 plus 2 retro 2 plus 2 process. It's going to be much easier to see it as I draw here than it would be to see it drawn here. So this is why redrawing molecules, specifically with mechanistic problems or synthesis problems, can oftentimes be really, really important, and why I really emphasize the artistic nature of this sort of topic. Okay, so if we do the 2 plus 2, right? But I have a triple bond there, so that would be my cyclobutene, but again, we have that double bond ring there. Or so it's a triple bond, so now it becomes a double bond, right? And then when we do the retro 2 plus 2 again, okay, now what we're going to get is we're going to get an alkene in conjugation with the ruthenium alkylate. Okay, so everybody see that? So let me, for the sake of board space, I'm going to redraw it over this way. Okay, so we have our ruthenium alkylate there. Okay, the end game should be fairly simple at this point, right? Because this is probably a fairly easy metathesis. It's probably good to sort of count the carbons here, but again, it's going to be for those same reasons. We want the sort of 2 going out, right? 1, 2, 3, 4, 5, 6 membered ring that we're going to have here. 6 membered ring that we have there. Right, so that's going to be following the 2 plus 2. Right? And then we're basically there, right? Because then all we need to do is do our retro 2 plus 2. And we're going to do our product, and then we're going to regenerate ruthenium alkylate. Okay? So, Again, certainly a challenging mechanism, but I would argue that the challenge of this one is, I like using TAPS as a mechanism because while it is sort of a puzzle and it is a challenge along those lines, the inherent actual reactions, the bond-forming, bond-breaking events should be fairly straightforward. They should be very easy for you guys to sort of see. So even those of you who have struggled with a lot of mechanisms, if you get down this 2 plus 2, retro 2 plus 2, at least you can sort of puzzle solve within the nature of this reaction. Okay, so what about the other way? If in the other case, so I'm just going to try and go through this one a little bit quicker, and I'll sort of take a quick shortcut here. But the other metathesis that we had was one whereby the ruthenium alkylidine ended up on this side, so we'll just sort of glance over the relay part of it, and we'll just start here for now. And as we'll see, it's going to be a very different looking product. So if we do the relay on the other side, we're going to get to this ruthenium alkylidine. And now let's go through the E9 metathesis, followed by ring closing metathesis, and convince ourselves of that, okay? So again, what are we going to do here? We're going to basically do that 2 plus 2. Okay, right away we notice a significant difference here, right? Because now the ring that's forming here now is going to be the 5-number ring that we see over that way. So if we do the 2 plus 2. Okay. Let's rotate around that bond. Once we do the retro 2 plus 2. Right, we're going to get to that compound that you're sort of seeing here. So let's just double check and count. 1, 2, 3, 4. 1, 2, 3, 4. I just rotated around the bond to hopefully be able to see it a little bit easier. And now the final bond that we're going to do is that one there. So what size ring is this going to be? 1, 2, 3, 4, 5, 6. Again, we have a 6-membered ring there, so that's a good sort of indication that that's what we should sort of have. So when we do the 2 plus 2, there, just right there. So just double checking. Okay. At this position, what we have is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. So at the 4 position, we have the methyl group. 4 position is the methyl group. 5 position and 4 position is where we have our ruthenium alkylidine, with the ruthenium basically being on the carbon of the 5 side. It's going to be that, right? And then we're simply going to do our retro 2 plus 2, regenerate our alkylidine, and go this way, okay? Now this is a metathesis cascade. It should take some time, so I get it. It takes a lot of time. It takes a lot of redrawing and so forth. And so it should certainly be a challenge to you guys, and it's certainly meant to be a challenge to you guys, but it's the same operation over and over and over again. Yeah? So the ruthenium on the alkyne, well, you can do that now, right? You can certainly do that. And so what I would then ask you is that if the ruthenium could go on the alkyne first, what would be the potential products from that? And what might be the selectivity? I believe, and you'd have to, and so I'd urge you to, actually that would be a good practice problem for you. And so, but off the top of my head, it seems to me that if you were to do that, you would likely get, I think, I'm sort of doing this mechanism in my head, I think that you would get to a situation where after the ruthenium alkylidine reacted with the alkyne, you would then get to the dienyl system. And what you would then have is a situation where you could do the metathesis on one way or the other, and then you would turn over, get more ruthenium, and then that would probably do the final metathesis. So you would probably get a mixture of the two that are in a non-selective process, although there could be other products as well. But go ahead and try it. I mean, that's one of the nice things about metathesis, right? So I did my graduate work at Boston College. And Boston College is very well known for the contributions that it's made in metathesis. The guy that I worked for, Mark Snappers, made some really nice work on ring opening metathesis. So if you've had a closed system, if you could say, for example, use ring opening metathesis, you could do some really cool stuff. One of the things that he actually did, which was really neat, which is actually really relevant to this course, actually be a really good exam question, was keep that in mind, is that he would do a ring opening metathesis and generate these dienyl structures that could then undergo Cope rearrangements. So both now reactions that you guys know. So basically you do a ring opening and then you do a Cope rearrangement and you generate these macrocyclic structures. So on the one hand, Mark Snapper, my boss, worked a lot and made a lot of contributions on ring opening metathesis. He also did some work on tandem metathesis. That's what I worked on a little bit, trying to get the metathesis to do other non-metathesis reactions. There's also a person there named Amir Haveda who actually has developed asymmetric metathesis catalysts. It's where he sort of started in this area, and then he got into developing actual catalysts that were much, much more stable thermally, and so you could do chemistry with these new catalysts that he developed. And so, again, a lot of really nice work there done. In metathesis, another person that was there, Scott Miller, that doesn't work on metathesis in his independent career. He works more on peptides, not really metals much. But he was also a graduate student, or postdoc, I forget if he was a graduate student or postdoc. I think he was a postdoc with Bob Grubbs catalyst, which is what we talk about. One of the Nobel Prizes was awarded for it. So there was a very big metathesis environment there. And when I started there and started learning about the metathesis reaction, I often found that it was really nice to be able to appreciate the level of complexity that could be generated through this reaction, through mechanisms that weren't necessarily all that out of the range of feasibility, and using your imagination to sort of think about some of these things. So, anyway, so that's metathesis. Definitely expect a question on metathesis on the final. Okay. All right, so we've got about a half hour. We'll do a Cope-Claisen mechanism. So before I do a Cope-Claisen, Cope/Claisen stereochemistry question, I have a lot of people come into my office and they start drawing these Cope-Claisen mechanisms, and they go through these chair transition states, you know, as we talk about the importance of drawing molecules, some of you guys, it's remarkable, you draw the ugliest chairs imaginable, but yet you can still see what's going on, right? So that basically means that you've adapted, you know, to be able to see things with not so great looking chair structures. But the other way that you could look at it is just draw a better looking chair structure, and maybe it would be easier for you to see what's going on. And so I just wanted to I sort of made this comment a few times in my office hours to people, and just something that I think is worth bringing up. And I apologize if I'm repeating myself, because I may have mentioned this in class already, but I think it's worth repeating again. You know, chairs, 3 dimensions, viewing things in 3 dimensions is obviously a challenge, right? We're aside from those of you that might have high artistic backgrounds where you're used to drawing things in 3 dimensions and seeing things in 3 dimensions, you know, it's really not a skill that's been developed all that much for the majority of you, and so it becomes difficult to see and envision 3-dimensional components in 2-dimensional piece of paper, right? So, but in organic chemistry, obviously, we live in a three-dimensional world. Chemistry exists in 3 dimensions, and so this is an important aspect of this course. And so the better that you are at drawing things, oftentimes the better it is to sort of see things. And so chair structures, you know, when we start to think about our chair structures, actually, that's when we start to think about the chair structures that we have, so I sort of just drew that straight up. But you'll notice that there's a few things in that structure. It's not a perfect chair, but what you'll notice is a few sort of things that make this at least work. And part of it has to do with the number of, a lot of just parallel lines and recognizing the nature of parallel lines and all these. So you guys recognize that chairs are basically the 6-membered ring, right, where all the bonds, right, throughout that whole system have all basically adopted a staggered conformation, right? And by virtue of that, as you guys know, from Newman projections, right, staggered conformations are nothing more than a series of parallel, right? You have a parallel line in the front that matches with the that's parallel to the group behind it on the opposite end, right? That's sort of anti-periplanar, if you will. And that sort of takes place all throughout that. It turns out that chair conformations are oftentimes much the same. And so when we think about the sort of parallel lines that you have in this structure, so obviously these are fairly easy to see, right? But again, these two parallel lines emanate themselves throughout the rest of the structure as well, right? So we'll have two parallel lines for the equatorial position there, and we'll have equatorial parallel lines at that position as well, right? We envision these two parallel lines there, right, that are parallel in nature. Well, guess what? Some of the substituents, right, are also parallel in nature as well. So that should be parallel to that, right? That should be parallel to that. So you basically have these parallel lines at those positions as well. And I'm out of colors, but fortunately white is okay. But parallel with this line, right, you then have the other equatorial position there, and the other equatorial position there. So all of these are all parallel to one another as well. So basically, that parallel nature can oftentimes really help you, specifically when we're talking along the equatorial plane. Fortunately, axial should be easy, right, because those are all up and down. So everything else that we have here is basically going up or down, so that's pretty easy to do. But yeah, so it's just, chairs are just a whole bunch of, effectively 3 sets of parallel lines, and then you have the sort of axial positions as well. Another thing that I would sort of mention really quickly, and this has come up as well in office hours on numerous occasions, so it's worth sort of bringing up. You guys will often draw structures where you'll just have 2 lines that sort of cross one another. And the problem with that is that when the 2 lines cross one another, it can be fairly ambiguous in terms of the 3-dimensional nature of that. And so anytime you have 2 lines that are sort of crossing one another, without a break on one side or another, what that often will suggest is either ambiguity in terms of stereochemistry and 3-dimensional nature, or what it actually sometimes suggests is that there's a quaternary carbon right where those connect, which makes it even worse, right? It tells you that it's not even an isomer of that, okay? And so if you have lines that are going to sort of break with one another, you oftentimes want that line there. So you'll notice this would be an example here, which is what you guys will often do. And so what we would want to do here is we want to put a break to those sides as well. Okay, so you sort of want to have the bond that's behind it sort of break a little bit so that the bond that's in front is the one that sort of sticks out. So in this case, I've broken this bond here, right, because it's on that side. And in this case, it's this bond, the green one that's in the back, that's really going that direction. So that makes sense? So again, I think drawing the chairs and drawing good chairs can certainly be very helpful. All right, so now that I've sort of given myself time to think of a co-pleasing problem, so I'm gonna throw a little. Actually, this might make it even easier. I'll just do a standard co-placement mechanism. We'll just go through it again instead of making it overly complicated because it's 6. Okay, so again we have the 6 groups there. Okay, so we'll put a methyl group there, and we'll put an isopropyl group at that position. And the question will basically be, this is going to be a selective co-rearrangement that's going to lead to a single isomeric compound. What is that single isomeric compound? And what this is ultimately going to boil down to is 1, 2, 3, 4, 5, 6 is that we're going to have stereochemistry You know what? I'm going to make it a little bit harder. Let's do that. And let's go ahead and see what the products do. Okay. So again, anytime that you're asked with a question like this, I think there's a number of places where people start to run into issues, and it's important that you try to simplify the problem as much as possible from the get-go, and put yourself in a situation where you're the least likely to have to do mental gymnastics, right? To get from say point A to, if it's from point A to point B, sometimes it takes a lot of mental gymnastics to go through that whole process. You want to sort of draw out all the intermediates as easily as possible. So we know that we have to get to the chair. And so what many of you will try to do is you will try to go right from the structure to a chair. And that's going to be very difficult because we really haven't learned, right, and you guys haven't really discussed how to draw, basically take a linear chain and condense it into a chair. What you have done, and what you guys do know how to do, and that you guys spent a lot of time practicing last semester, was how to take 6-membered rings that are flat and turn those into chairs. And so that's why one of the first things that we want to do in these problems, sort of make our lives a little bit easier, is to take this molecule and start to make it look more like, put it into that sort of start making it look a little bit more like a 6-membered ring. So that's the first thing. The second thing that people try to do, okay, so then what people will often do is this, right? So then people will go ahead and they'll just draw the co-product. I say this because a few people in my office have done this, and I realize that it often will cause issues. And then they'll sort of look at it and they'll be like, okay, so I know that I need to get to this, so they'll just start by drawing this. And that can be okay, but now there's still a certain level of mental gymnastics that have to go because you have 2 stereogenic centers. You have to start to figure out what they are. And you can do that, and there's ways that you can do that. I think what you would want to do is you'd want this carbon to be this carbon, simply because if you look at how this is going in this direction, alkene, this is going up, that would be fine. But I think more generally, so you could do that from that. That's not impossible, but mistakes tend to happen. I think the better thing to consider is keep it looking sort of like it is already, right? At least in part of it. Keep one stereogenic center constant and sort of move the rest. And so if we dissect the molecule, what we realize we need to do, right, is we need to rotate around these bonds and in essence get those 2, in terms of what we eventually want to do that we can take home from this, right, is that we want to get these 2 basically syn to one another, right? We want them to be effectively eclipsing in a way. But to sort of start moving everything around might be a sort of challenge. But what if what we did was, that's easy to rotate around, we don't have to worry about anything there. But if we hold part of it the same, right, and start asking the question, all right, I know that I want to hold this the same, so I'm just going to redraw that the same. If I was going to redraw it exactly the same, it would be that, right? But I can rotate around this bond, no problem. It's not going to disrupt the stereochemistry because it's just moving the alkene into the appropriate position. But I do want to rotate around this bond to get this alkene down, right? And so now the question becomes just one stereocenter, and you've sort of drawn it in a way where you can now begin to rotate around that bond. And it's still going to be a little bit of mental gymnastics, but it's a little bit easier perhaps to see, and it's perhaps a little less daunting. Okay? So at this center, sometimes it's worth it to draw the proton as well to help you, right? But what we're doing here, right, is if we think about like a Newman projection, for example, and I'm not going to go ahead and draw the Newman, but just to sort of envision in here, what we're doing, right, is we're rotating around 180 degrees down this bond, right? It's this group has to come all the way down there. And when we do that, we're going to move everything around 180 degrees. When we do that, this group's going to be going down. These two groups are now going to be coming up. Okay? And all that we need to do here is we need to figure out which side of the molecule now the proton is in and which side the methyl group is in. And if you just sort of think rationally and logically, when we rotate around that 180 degrees, that methyl group, which is now going down that way, 180 degrees from there, is going to be coming out towards you guys that way, right? So in the same way that the 180 degrees from here down to there basically moves it down, that methyl group from there, 180 degrees from there, goes in that direction, okay? So the methyl group is going to be coming towards us, okay? So, and again, I know that some of you guys will basically see this over and over and over again, and you'll start saying, okay, all right, if they're going the same direction, then I'll just make them go in the opposite direction when I do it next time. And that'll work for you sometimes, and you might get lucky, but I think that you may be thrown with a slightly different question in a slightly different way where those tricks might not necessarily work. So the tricks fall apart fairly easily, but if you can see what's going on, then it will make your life a lot easier. Okay, so now we have the molecule looking something like a chair, right? And this is where you guys have gotten pretty good from all that work on chair conformations to be able to take a 6-membered ring and convert it into the chair. And so you guys will often do this. You'll number your carbons, which is good. And what you'll very often do is you'll go ahead and draw a chair conformation just to sort of help you start your way. And then you'll go around and go 1, 2, 3, 4, 5, 6, right? And then you'll start filling in the blanks, right? So you'll say 1 and 2. Sorry, 1 and 6 is where I'm making the bond. 1 and 2 is an alkene. At the 3 position, I have an isopropyl group. Where's that isopropyl group going? Axial, good. Right, where's the methyl group going? Equatorial. Right, and then the 5, 6, we're going to have the alkene. And so this is one chair conformation that we have. And so some of you will go right to the one chair conformation and you'll take it through to the end and you'll say, that's my answer, right? But what you have to recognize, and this is the case as we have drawn here, that perhaps this chair conformation might not be the best chair conformation, right? And what might stick out about this chair conformation right away when we look at it that might tell us that there might be a better conformation that we can have? Yeah, well, it's isopropyl, but the bulkier of the two groups, the isopropyl is bulkier than the methyl group. And so of the two options, we could put the isopropyl group axial or we could put it equatorial, and we'd probably rather want to put it equatorial, right? So this is a good chair conformation, but when you look at it, you say, okay, the isopropyl group is axial, I probably don't want the isopropyl group axial. Can I draw a chair conformation where now the bulkier group is actually going to be equatorial? And so what do? We go ahead and we draw this sort of chair flip of that molecule. Again, we have to sort of be careful here when we draw the chair, because a lot of times what you guys will do, and so this is just be forewarned, that when you guys do this, it's important that you number it the appropriate way. It's not uncommon at all for when you guys do this to simply just, when you redraw it, you rotate it just a little bit. You don't even realize you're doing it, but you just end up rotating it a little bit, and then everything ends up in the same positions. Yeah.
I was wondering, the coherent arrangement of the fives, are they mostly for 6-numbered rings, or can it be like less?
No, it's Cope and Claisens have to be, yeah, it's a chair transition state.
Okay, so it's only 6.
Yeah, I mean, there's other pericyclic reactions that you can imagine where you can do similar types of sigmatropic processes, but those aren't Cope and Claisens. Those are just sort of, you know, electrocyclic processes that might be, you know, like there's reactions called like electrocyclic ring closures that look similar, but you can have those be like much larger amounts. But anyways, so the point that I want to bring up here is that if what people can do, right, fairly quickly here, and the mistake that you can make is that when you go ahead and you start numbering this, you can look at that one that you numbered 1, and it would not be uncommon at all for the person to look at that 1 and they'd be like, where does that end up there? And they'll just pick that position. But that's not going to give you the right answer, right? And part of the reason that you can sort of know that is, notice how this is going up, and this is still going up. You want to make sure that when you do the chair flip, that this is the position that's actually going down. So this 1 is actually here. Does everybody see that? So this should be 1. It's not a common mistake that when you are being really careful and you're drawing all these things and then you just make one stupid, I'll say stupid, but just numbering mistake that throws off everything. Yeah?
So you leave your break in
The
between
one.
right there.
Yeah.
If you were, let's say, move it to, yeah,
Yeah, you could have done that as well.
and then it would be as within 1.
So that's actually good. That's I actually kind of like that. So I'll come back to that once we do it this way, because an alternative strategy, actually that might be a lot easier to do. I hadn't really considered that. So let's come back to that. Remind me. Don't let me move on. So anyway, so if we go ahead and number these, right? Now what we're going to have is we're going to have that 1,6 bond. Right, we're going to have that alkene. Now the 3 is what? Equatorial, right? It's going to be up equatorial. And the methyl group is now going to be up axial. Right? And then we have our 5,6 double bond, okay? So now, oh man, we're not going to have enough time. So anyway, so from here, what you guys will then do is you'll do the rearrangement. Right? This will be the sort of rearrangement product. And when we do that, what we'll sort of notice, right, is that the methyl group, which is axial, in the product it becomes cis, and the isopropyl group, which is equatorial, becomes trans. And that's common. When it's equatorial in the chair, it becomes sort of it becomes trans, and vice versa. But somebody, Amanda just brought up something that I thought I hadn't really considered, but actually would work. So she asked the question. She said, "Okay, well, you broke it at the 1,6 here, right? But couldn't you get that same effect that we had here? You're saying you might just move it a little bit."
Just change your numbers, essentially.
But yeah, can't you just change your numbers around, right? If we know up here is axial at 3, and we know that up here is equatorial, why don't we just move our numbers around and we'll get there? And I think that's great. I hadn't considered that, but that's fantastic. Bonus points for you. But yeah, so what would happen there, right, is that the 2, 3, now basically we'll just sort of move it around. So these will be here. The 3 will be here. So now we've got 1, 2. The 3 will now be here. Right? The 4 will now be going up methyl. right? And you'll get to that sort of same thing. So that's another way that you can do it. Rather than draw a full sheriff flip in principle, you can just change the numbers over one. I think that's great. I hadn't considered that, but that's definitely something that you can certainly do. So yeah.
So your number of RNS, if I number RNS the original there, what comes first, a double bond or the two RNS?
So you treat double bonds as two carbons. Once you get to the end of those two carbons, they have H's. Now, if you're dealing with a carbon bonded to two methyl groups versus a carbon double bond that then at the end of that becomes CH2, I actually don't know. I would guess that a terminal alkene would probably come after an isopropyl, simply because you're counting each of those bonds separately. So when you do the first bond, you go CH-CH, and then the other one would be CH-CH. The other one would be CHH, CHHH. So in terms of the priority, I would guess that it would be, okay, H's are the same, H's are the same. Now I've got an H here where I don't have anything there. But I don't know. But for your, what, yeah.
Does it really matter? Because if you give it priority 1, let's say.
Yeah. So, but from the IUPAC standpoint, I don't know. I don't know what the IUPAC standpoint is. But the point that was brought up is that for checking your answers, it doesn't really matter whether you label it RRS for the purposes of double checking your answers if you stay consistent. And RRS is, again, stereochemistry is important. Whether something is RRS and your name to it is not really all important. Okay, so, all right, so again, exams are going to be Monday. Make sure that you get here early. I've gotten quite a few emails. So my plan is regrade requests. If for whatever reason you ended up getting your exam back, it only should be a few of you that contact me. But if you're one of the few that's been in contact with me that got your exam or part of your exam back late, feel free to just try to get me a regrade. If you decide that you need a regrade, just try to get it to me before the exam. For the rest of you, what I'm planning on doing is looking through all of those probably tomorrow morning before the science retreat. Please don't just check the Blackboard over the weekend because I should have those up. If there isn't a change, if it's one that was sort of up in the air, then I probably decided that it wasn't. But you can certainly ask about it. So, all right.